Welcome to this explainer, where we're going to dive into how MLflow takes chaotic machine learning workflows and transforms them into perfectly structured, automated pipelines. Whether you're just running a simple linear regression on your laptop or you're deploying a highly complex generative AI agent in production, keeping track of your code, your parameters, and your models can easily turn into a massive headache. You know, the kind where you accidentally overwrite your absolute best model checkpoint at 2 in the morning just because your files were a total mess. Well, today, we're going to look at how to completely eliminate that friction.
We have all been there. You run dozens of experiments, you're tweaking your hyperparameters, and suddenly, you realize you've completely lost track of that one winning model checkpoint in some messy, untitled notebook. It's incredibly frustrating, and honestly, it wastes so much time. So what if you could track your entire pipeline with just one line of code? Imagine replacing dozens of lines of manual, tedious logging with a single, elegant command.
Section 1. One line of code.
Let's start with the microscopic pain of manual tracking and how we instantly cure it. Going from zero to fully tracked is incredibly fast. First, you just grab MLflow using a quick pip install. Second, you drop in that single line, mlflow.autolog, right before your training code. Third, you just execute your run exactly like you normally would. And finally, you launch the UI with the MLflow UI command and head over to your local browser. Suddenly, without writing a single custom print statement or manual artifact log, your entire experiment is beautifully organized in a graphical interface. It's really that simple.
Now, think about the sheer volume of tedious, error-prone manual logging you're never going to have to write again. By calling that one function, MLflow automatically captures your metrics, completely tailored to whatever library you happen to be using. It grabs all your hyperparameters, and get this, even the default ones you didn't explicitly set. That's a massive lifesaver because silent default changes in library updates are basically the #1 killer of model reproducibility. It also logs the model's signature, so you know exactly what input and output schema your model expects, securely saves your checkpoints as artifacts, and even tracks the dataset object you use for training.
And this adapts perfectly to your tools. Say you're using TensorFlow and Keras? Well, MLflow just knows to grab your training and validation loss, and it'll even save your TensorBoard logs. Working in PySpark? It automatically grabs your evaluator metrics and the fitted estimator. Or if you're building traditional machine learning models with scikit-learn, it seamlessly records your estimator scores and the fitted models. You don't have to explain to MLflow how to track these different frameworks. It literally natively understands the dialect of the tool you're using.
Okay. One quick caveat to keep in mind depending on your infrastructure. If you're running your workloads on Databricks serverless compute clusters, auto-logging functionality isn't enabled by default. So you do need to explicitly cast this magic spell by calling the MLfo.autolog function yourself right in your notebook to trigger the tracking.
Section 2. Scaling with tracking servers.
So local tracking is fantastic for individual discovery. But let's be real, data science is a team sport. And this brings us to the MLflow tracking server. By simply running the MLflow server command in your terminal, you instantly graduate from a local SQLite database file to a centralized mission control. Now multiple users can log their runs to the exact same endpoint. This means you can query models logged by your teammates, share a centralized UI to explore results side by side, and effectively secure access to all your metadata.
Now, by default, your tracking server listens only on localhost, meaning only your local machine can talk to it. But by binding the host to 0.0.0.0, you're telling the server to listen on all available network interfaces. This is an absolutely essential configuration step if you're deploying your MLflow server inside a Kubernetes pod or a Docker container, where those network interfaces actually need to communicate externally with the rest of your team.
Of course, the minute you open your server up to the network, security becomes paramount. MLflow 3.5 and above automatically shields your internal services with built-in security middleware. It provides DNS rebinding protection to stop attackers from hijacking your internal IPs by validating host headers. It offers CORS protection to make sure only authorized web apps can hit your API. And it uses X-frame options to prevent malicious clickjacking, which is where an attacker might try to trick a user into clicking something dangerous on a hidden page.
Section 3. Securing your ML artifacts.
Let's move to the architecture and see how we build an ultra-secure vault for your most valuable model weights and datasets. You basically have two architectural choices here. Think of proxied access, kind of like a valet service. By starting your server with the artifacts destination flag, the server manages all the AWS or cloud credentials. The client just hands the keys to the server, meaning your data scientists don't need AWS keys sitting on their local laptops. On the flip side, direct access is more like self-parking.
Clients bypass the proxy and talk directly to your cloud storage. Now, this might be faster for massive files, but it means every single client machine needs its own direct security credentials.
And hey, if you're operating at true enterprise scale and your system is getting absolutely hammered with concurrent requests, you can actually spin up a dedicated server just for heavy artifact lifting. By starting an MLflow instance with the artifacts only flag, you isolate the compute-intensive job of uploading massive model weights from the lightning-fast requests querying metadata. This keeps your user interface incredibly snappy and your infrastructure highly resilient, even under massive load.
Section 4. Tracing the GenAI future.
Okay, let's dive into the cutting-edge realm, because classical models are really just the beginning. Generative AI fundamentally changes how we track applications because the outputs are no longer just simple numbers or lost metrics, they're complex, dynamic conversations. But with that same magic one-line philosophy, we can now peer right inside the black box of multimodal GenAI models. If you're building with OpenAI, LangChain, or LlamaIndex, you simply call the corresponding autolog function, like mlflow.openai.autolog. Instantly, MLflow sets up tracing, capturing the intricate back and forth between your application and the language model.
Just look at the wealth of context you get right out of the box. It captures everything from the exact text of your prompts to the model name and metadata like the temperature setting. If your AI agent goes rogue or hallucinates, you can see exactly why. It captures function calling instructions so you know exactly which tools the agent decided to use. It even handles complex deployment patterns seamlessly, like tracking asynchronous API calls and beautifully stitching together chunks from streaming responses into a highly readable trace UI.
Now, because GenAI applications generate a massive amount of verbose trace data, especially when agents get stuck in conversational loops, your database can fill up fast. To solve this, you can set up a YAML configuration file to literally sweep older traces into archival storage. This trace archival scheduler ensures you keep your active tracking database lightweight and your UI fast without actually losing any of those historical traces for long-term auditing or fine-tuning future models.
Before we wrap up, I want to share a quick but absolutely vital best practice for the GenAI era. Never, ever hard-code your OpenAI or Anthropic API keys in your tracking code. When you're pushing these traced applications from your local notebook into production, always use a secure secret manager, like MLflow's AI Gateway or Databricks Secrets, to authenticate your LLM calls securely.
So I want to leave you with this thought as you head back to your own pipelines. As your models evolve, is your observability scaling automatically, or are you still manually logging? The leap from classical machine learning to GenAI agents is massive. If your tools require you to write custom logging code for every new prompt, tool, or API parameter, you're honestly going to get left behind. By using MLflow's automated tracking and secure mission control, you can finally stop debugging your logging code and get back to actually building the future. Thanks for joining me on this explainer.